be. Thank you. 3 GeV result we presented already at CPOT 2021 and SQM 2021. Here is a plan. After a very brief introduction, I will discuss a little bit star experiment, then move on to some results. I will focus on collectivity and criticality. Those I think are important physics for heavy ion collisions at high energy. I call them emergent properties of strong interaction. Then I'll discuss a little bit what should we do in my personal view in BS2 and beyond. So that's the plan. By the way, if you want, stop me anytime. So this is perhaps the only theory slide I will show, and this is the lattice QCD calculations. We have a critical point, which is showing here, TCEP, and we have a critical, this is a QCD transition temperature. This transition is from QGP to hydronic matter. This is very precisely well defined. So that is, I think, is an important point. That is showing here. I should mention this is temperature as function of baryon chemical potential, and also as function of UD quark mass. So basically, if this goes to 0, it's indicate the chiral symmetry restoration. So this transition is actually chiral transition. So those are details I'm not going to mention. Another important point I would like you to remember is at least now lattice says when mu b divided by t greater than 3, that's a region. Below that region, actually, there's no indication of a critical point. So the region is beyond that when it would maybe the critical point. So that's very important. One point is this TPC temperature, the transition from QGP to hydronic matter. Another is the critical point, so excluded region. That's I think two important things. Now, how to study this QCD phase diagram? We use a star detector. I guess you're very familiar.
Oh no, sorry, interrupt. So I think the prediction you mentioned last slide on the lattice QCD, it's a very important one. So this only hot QCD prediction. Any other group also?
I think the other collaboration also consistent. What is only different now is here. For example, one group said specifically is greater than 2 for sure. So I used a little bit of loose region, more excluded region. So that's all as far as I know, these messages are consistent from these 2 energy points. Yes. And I just pick up 2 hot QCD publications.
Okay, is any additional evidence that, for example, the baryon density below than certain temperature, there's no critical point? I mean, maybe I don't know. I mean, this of course the lattice calculation. Is any other way you can also verify this experimentally or theoretically?
Yeah, I will show you experimentally how to do that. It's theoretically, if you ask me, maybe I'll make more enemy. I do not. I trust the lattice calculation most. So this is to me the guideline.
Okay.
Gotcha. And this number extracted is from, they take their calculation only can be done precisely at mu b equal to 0. Then they do Taylor expansion. So how far they can push depends on statistics. So early on was 2, now we move to 3. So that's roughly the region.
Yeah, maybe if I can make a small comment here, I think at SQM, this question also appeared in the latest talks, and they emphasized that they disfavor critical point at small mu b over t, but they do not exclude it completely. It's a disfavored region.
Okay.
Small mu b over t. It's not excluded.
That's good. I think this comment.
I think that's what you heard. The disfavor. disfavor, I also heard unlikely.
The same thing. I mean, disfavor or unlikely. Yeah.
All right.
But not 100% excluded, for example. I don't think they can put some kind of, for example, 1 sigma or 2 sigma or 3 sigma or something, or computation level to
right.
really...
Yeah, because they need to know this high order terror coefficients, how they behave, and they cannot calculate them to arbitrary high order. So there's only so much you can do with this method, maybe. Yeah.
Especially when you get a large mu B region, the uncertainty becomes huge.
Yes.
Yeah.
Okay. Thank you.
So this is a detector I'm not going to discuss too much in detail. The real feature of this detector is large acceptance and a very good particle identification with uniform efficiency. Another feature I would say it's a modest rate. The rate is not very high. That's a star detector. Yes, please, people ask questions. If you have questions, please ask. Now, the additional piece beyond this general beautiful star detector is this called the so-called fixed target mode. So what star did was put a piece of gold at a 1% interaction length at the entrance one side of the TPC. And so this is a fixed target mode. And in the opposite side, star add additional detector, time of flight detector, end cap time of flight detector. This is actually borrowed from CBM experiment. So this allows us to extend the energy from 7.7 GeV, which is the end of the collider energy, to 3 GeV center of mass. And that's actually very important because at the 7.7 GeV central collisions, mu B is 420 MeV. If we go to 3 GeV, it's around 750 MeV. The number is roughly there. So we do have a number, but not in public yet. It's around 750 MeV. And this is very important for us to study the medium at high baryon density region. So that's why I especially mention it here. With this detector, we have excellent particle identification, as I said already. This is a TPC for particle identification, pions, kaons, protons, and other heavier particles. For TPC, it covers for protons, for example, at a little bit shy of 8.8 GeV, then we have to use time of flight in order to clearly identify protons. And this is identified kaons, K plus, K minus, pi plus, pi minus. For proton, which is my focus for the critical point search, the coverage is plus minus 0.5 unit of rapidity, and PT is from 400 MeV all the way to 2 GeV. So that's our acceptance. We're working within this region to do it. The efficiency, if it's TPC alone, it's about 80%. If we add the time of flight due to the coverage, and the efficiency is about only 50%. So that's the setup we use to do the analysis. I'm going to show later. Now, those are the collected energy for beam energy scan 1. Highest energy is 200 GeV, all the way down to 7.7 GeV. In 2018, actually this year is neither beam energy scan 1 or beam energy scan 2. We took a fixed target run with 3 GeV as a pilot run. So roughly we collected 250 million events, 3 GeV, and this is roughly mu B and temperature. This is, I put this number here because in this discussion, I will use some of the 3 GeV data for the discussion. As you can see from the right plot, from 7.7 GeV, those are collider mode, to 39 GeV to 200 GeV. The particle for pion, kaon, protons, the acceptance are uniform, and it does not change when energy changes. Also, when you change the particle type, the change is also minimal. So this is a very good advantage for the for the fluctuation analysis. It's very important. When we move to a fixed target, actually we lost this advantage.
No, a stupid question. How you determine the temperature?
This temperature, okay, that's a good question. We take a thermal model to put particle yield to fit extract the chemical freeze-out temperature. And if you want, this is example, this paper, PRC. This is just rough gauge here. Assume there's a thermalization.
So naively, so this is just because your energy is not high enough, so particle just fall off more rapidly. Is that right?
It's also system is not hot enough. The energy is low, and it's actually the in terms of time evolution, actually for 3 GeV, as far as I know, lasts a little bit longer because pi n interactions keep the system longer time.
Okay.
Yeah, hold on. Let me get a dog out. So actually, otherwise it will keep barking. All right, sorry for that. So this is the data set we use from B-scan 1, and we analyzed all of the data. So the last one was 54.4 GeV. We took 1.2 billion events, actually important events. Now, before I go to every details, I just want to give you a global picture in terms of the global properties where we are. So this is the chemical freeze-out temperature as function of baryon chemical potential. Red circles are from central gold-on-gold collisions. Open squares from peripheral collision from star. So you can see that about actually relatively flat all the way to LHC, at least result. The temperature doesn't change much. And mu B change a little bit from central to peripheral collisions, which naturally we understand. For fixed collision centrality, mu B is larger for central collisions due to more stopping. In the middle plot, I show you K plus over pi plus ratios, and also K minus over pi minus ratios. For the plus, there's a peak around 8 GeV. And we understand this is due to because the baryon density reaches the maximum at freeze-out at 8 GeV. And this actually is reproduced through this model analysis. This 4 plus 4 is also around 8 GeV. You see the density at freeze-out reaches maximum. So this is indication of the baryon stopping for K plus. This is doesn't affect the K minus because K minus is produced via pair production, not involve baryon. K plus has a very strong, also large cross-section, low threshold associated production. That's why we see this peak. Thermal model fits can roughly, I would argue, reproduce both processes, both K plus, K minus. So this, so in the future discussions, I use this 7.7 GeV or 8 GeV. Below this region, I call that high baryon density region. I think that's an important region. And above, pair production becomes dominant, like the low baryon density region or meson dominant region for this study. Now let me move to criticality. So so in strong interactions, we know baryons charge and the strangeness are conserved. So we can use this conserved quantities to looking for possible critical behavior. Those quantities are also very important. Advantage for that is it's sensitive to a correlation and also of course phase structure. As I discussed later here, this is also directly make a connection to theoretical calculations. That's why I think it's very advantageous. So this is a definition of the the observables we use, and this is multiplicity. We measure n, and delta n is n minus mean value of n. Variance, skewness, and kurtosis. This is just basically the definition. The advantage it shows here is that if you take the combinations of these moments or ratios or products, you can directly connect it to the ratios of a culminant. And so that means you do experimental measurement connected to culminant. Then most relevant, I think important is this actually connected the theoretical calculations, ratio of susceptibility. First order, to the first order, the volume fluctuations are canceled out. So that's why in 2008, we had a workshop at INT, adopt this, this approach using high moments to study the fluctuation behavior. And here, because we do not measure all the baryons, event by event, cannot, or efficiency is very low, we use protons as a proxy for baryons. So today I will not discuss charge nor strangeness, so they are not discussed here. Okay, so this is actually, I think, still very important since 2008. Now I show you one model calculation at what do we expect from such measurement. For the first order, this is a paper by Misha Stepanov in 2011. He predicted that if you change energy from high energy to low energy, the fourth order, this is kurtosis again, will show a dip, then rise the peak, and come back to this baseline. The baseline is one. If nothing happens, you just follow this baseline. Of course, this assumes system is in equilibrium. This itself is a question. If we look at the phase diagram, you can see this way, when we lower collision energy, we increase the UV, and gradually this black line is the freeze-out line shown here. So the blue point peak here maybe is the closest or proxy to critical point. So this is this kind of, I call the oscillation, is what we hopeful to see experimentally should the critical point exists. Yeah, so this sometime I call this is actually when we see start the onset of the oscillation to see disappearance, and this is the, I call that a critical region. So this is important. Another important concept is this baseline only means non-critical. There are non-critical dynamics. So baseline not necessarily flat, as we will see in the discussion. So that's the important point to remember. Now,
another stupid question.
Sorry, I did not hear you. Yeah.
Another stupid question. So if your freeze-out line actually very much away from your interest region, so that means there will be no way you actually can experiment.
Agreed.
Okay.
Yes.
Okay, I just want to confirm that.
if the system far away from the and because the risk gatherings, the signal will be diluted, washed out. Yes.
Okay. Okay, got you.
Yeah, completely agree. Makes sense. Yeah. So this is the centrality. Centrality definition. We measure from 7.7 GeV to 200 GeV. The blue covered region as a top 5.
Now, if I may ask question, if to what Feng asked, I thought that the belief is that if you are missing this criticality, this critical point by 100 MeV, you still will see it. So it's not like you have to be on the point. There's an area that there's still going to be significant signals that you cannot miss it, right? Is this 100 MeV is not any more estimate of the region of sensitivity?
I think my answer would be the following. Because this is microscopic interactions, or this is very called asymptotic, so very stochastic. I don't think we can say there's a point of a critical point.
Right. But when we were deciding about step, in
Number
beam
two.
energy scanned.
Yeah.
In energy, that was one
Yeah.
of the criteria that we didn't want to have a too big difference in energy because we wanted to be able to be sensitive to everywhere. And the assumption was that you really feel the signal even if you're 100 MeV from the critical point, right?
I do not know any calculation can tell us how many MeV away we can have sensitivity or not. Either way, I'm not aware of any. There's no model, no theory, first principle theory calculation. Only this is, I say this is one of the models. Okay, so we do not know. For example, where does this happen? There's no number. Where, how far this how high go above the baseline, and what is the depth of the minimum? Nobody knows. I do not know. This is still experimental driven. So yes. Okay, so comparing this charge particle multiplicity measured in the detector and compared with the global calculation, we can determine the collision centrality. So that is very important. In all this analysis, actually took us many years. We did lots of corrections, including centrality beam correction, because we have to remove some of this volume fluctuation. Collision is not fixed. And we do efficiency corrections and also statistical uncertainty estimation. It's very involving for high orders, especially. And also for the fixed target case, the pileup correction is also very important. So those corrections so far, we done quite well, except the fourth one. I think we only can do most central collision now. For peripheral collisions, we're still struggling with that, but that's a different story. From the beam scan one, for this energies, we measure this is net proton distributions from the most central 5% central gold collisions. And the most right here is from 7.7 GeV, and gradually we move to the top 200 GeV. So you see, because of stopping, so when you lower energy, you have more and more protons, and the distribution becomes broader. So from these distributions, we can extract all the coordinate, different order of coordinate. Then we construct the correlation functions and ratios. So this is the centrality and energy dependence of the cumulants C1 all the way to C4, from 7 GeV all the way to 200 GeV. So from this, actually not much we can see. It's just all these numbers shown here. In this, only here I should mention this 2 points we actually suppressed by factor of 2, otherwise too far away. Otherwise, all this data are good. Then here I show you the energy dependence of cumulants for C1, C2, C3, C4 from most central collisions and peripheral collisions. So in all cases, you can see peripheral collisions basically is flat as function of collision energies, but we do see clearly energy dependence as function for the most central collisions. So that's actually important message from here. Now let's take ratios, and I show you here the skewness and kurtosis. This is basically C3 over C2, and this is C4 over C2. So if we look at the energy dependence for C4 over C2, as you can see clearly, there's energy dependence for the most central collisions. At around 20 GeV, we see a minimum, then go to lower energy or higher baryon density region, you see gradually increase. Statistical uncertainty is here dominant. So we still need more data in order to see anything really happen here. This green is our projected statistical error from the beam energy scan 2. That's what we are doing at the moment. We're taking data now. Again, for peripheral collisions, this is flat. Nothing happens. And we also applied made a plot from URKMD calculation. URKMD is a transport model. There's no critical behavior. So this is shows us the yellow band here. We understand that this is suppression going down to low energies because the measurement is done with plus minus 0.5 unit rapidity beam, so it's fixed. When you go to low and lower energy, relatively you put stuff more and more baryons into the same window. Therefore, the baryon number conservation will play a role here. So that's why it caused this suppression. So it's very relevant. So, but it's different, the behavior from the data side. So URKMD, if we calculate the peripheral collision, that is consistent with the open squares here. Now for the at 20 GeV, if we see if there is a suppression that is due to a suppression for 7.7 GeV, seems to indicate there's attraction. So this is to me the important element for possible exist of a critical point. That's why we are very excited for this point. Took us about 8 years to finish this data analysis and publish. So it's very important. Before I move on to more statistical analysis of the data, I want to show you a recent result and to higher orders. So this result actually reported in CPOT and also SQM. So what we show here is a C4 over C2, C5 over C1, and C6 over C2 from proton-proton collisions. That's these red dots shown here as function of multiplicity, charge particle multiplicity. The blue, shining blue circle in the middle is the averaged one. So this is for C4, C5, and C6. You can see they're all above 0. That's very important message. And we also plotted the result from gold-on-gold collisions at 200 GeV. Those are showing as the triangles here. For C4 over C2, they're all also positive and consistent with the lattice prediction calculations. But for C5 and C6, we see gradually when we move from peripheral collisions to central collision, they become negative. Same for C6 over C2. Progressively, they become more and more negative. This is exactly predicted by the lattice calculation. If you have QCD matter produced and you have a smooth crossover, you would expect this negative values. The caveat here, I show here is lattice calculation for net baryons and for infinite thermalized system. Here data measurement is for net proton. But I think this is the first time really heavy ion collision results compared to the first principle lattice calculation directly. So this, I would say, it's called direct evidence for the QGP formation and the transition. I think it's a very important measure. So this is the lattice prediction. These two bands, just C5 and C6, this is negative for high energy collisions. They actually predict that down to all the way to 39 GeV, but we only have data from 200 GeV collisions. Sure, but this itself, centrality dependent to me already very encouraging. So I think, yeah, I'm very happy about it. So now come back to C4 and C3, C4, and from gold-on-gold collisions as we published recently, we took this data and we did a statistical analysis of for both second order, third order, and the fourth order. I only show you, for the short paper, we only show the third order and the fourth order. So for the fourth order, we actually have a 3.1 sigma that indicate this is actually non-monotonic behavior. The reason I emphasize this is because it took us a long time, almost a year long time, discuss with the referee whether this is significant or not. So I'm not going to argue whether significant or not. It's just the outcome of the statistical analysis. For the third order, actually, for non-monotonic, only up to 1 sigma. If we look at the second order, it's actually monotonic. We see monotonic behavior. This is consistent with the argument saying if there's a correlation length, because it's very small, and you have to go to high order in order to see if there's anything non-monotonic as the critical point would lead to. So that's I would say it's an important piece of evidence for the non-monotonic behavior. We also compared with all possible models that calculate the energy dependence in, for this is a fourth order, second order, third order, and the fourth order. So we use the hadron resonance gas model. This is a ground canonical calculation, and this is a canonical calculation. All the references are listed below. And this is also ground canonical, but exclusive volume calculations. And this is URKMD. In case of 7.7 to 20 GeV energy range, we all observe this much less than 0.005, meaning they are not consistent, because all model calculations predict the monotonic energy dependence. As I showed you URKMD, but actually the canonical behavior is very close to RQMD. I should mention, I cannot just say that we did this, is right. There are also on the literature, people use this to a much wider energy range. Then they found that at some point, the fourth order is consistent with monotonic. But our argument is if you go to high energy, that means you always approach that non-critical, move away from critical region. Of course, you should see a smooth behavior. If you go to even higher to LHC, you will not see by definition, at least in the fourth order in this case. That's our argument. And so the conclusion I take is we do see in this energy range non-monotonic behavior. So if that is not enough, so what I did was, oh, it's not here, next page. But we also did a comparison with lattice calculation. So let me just focus on C4 over C2. I just fit with lattice function C4 over C2 like this. So this is the fit down to 20 GeV. This is I plot with C1 over C2, which is lattice like to do. So then we do not have to introduce additional parameters here. So, but the corresponding mu b or collision energies are listed here. So here's the highest energy, smallest mu b, or smallest m1 over sigma squared. You see lattice is consistent down to 20 GeV. This is 19.6 GeV. But a higher baryon density region or low energy, we do not fit at all. URKMD in yellow and this brown color is from canonical calculation. They are consistent. So the ground canonical basically is flat. So in this sense, URKMD lattice calculation again is consistent in this high energy region. So that's no issue. Same as we observed in the C6, C5 case. Now I also took this model. We can calculate the deviation. The deviation definition is shown here. I took most central collisions, fourth order, and subtract off the reference. Reference I list here from HRG. This is a ground canonical model calculation. URKMD, this is similar to ground canonical also. So this represent both canonical and the transport model, and also peripheral data. Peripheral data to me also shows non-critical behavior. So you can see from this, the sigma is just errors from both statistical and systematic error added in quadrature. So you can see it's also between 2 to 3 sigma in around the 20 GeV region. So this is, the hope is from B- scan 2 in this region, we'll also get more than 5 sigma result. Either way, hopefully we'll see that. the deviation from 0. So that is, this plot is not published anywhere. We're waiting for data to see how many sigma we can observe in this region. So all this, what I want to say is we do observe non-monotonic behavior in a region. The critical behavior might happen. So that is for high energy. We also, as I said early at the beginning, we took 250 million gold-on-gold collisions at 3 GeV. So this is this result is not available for public yet. I only show you the URQMD calculation for protons is around -1. Data is consistent with it. So what does this mean? That means actually if we fit this with oscillation pattern, this curve actually really comes down. Okay, that means that it's disappeared from the critical behavior. So if we follow this gold yellow band, that means this is only the, I call the dynamic baseline. That's why we keep calculating URQMD give us, we know where, if there's no critical behavior, it should behave like that. So this is very important. Now, between 3 GeV and 7.7 GeV, there's a gap actually here. Although star fixed target data also fill this region, but we don't cover middle ability. So it's very actually troublesome. That's why I said we need to actually move to CBM experiment at FAIR. So the point to take from this slide is that 3 GeV looks like critical behavior disappear. Hadronic interaction dominant because URQMD is all hadronic. This is also supported by recent publication from Hades of proton measurement with a little bit different kinematic coverage, but error bar is huge. So if you look at the phase diagram I draw here, so the region, focusing the region search must be between mu b over t equal to 3 to mu b equal divide over t is about 7. This is a region we should focus, try to narrow down where the critical point or critical region is. So this is from the collectivity point of view. Now I guess I will move on to some collectivity. So here I'm not really talking about collective flow or things. I just want to use this also as a tool to study medium properties, so help to build up the case. So flow is important. We know that for 20 years already, because it's a convert coordinate space anisotropy to momentum space. In the process of transition, we can extract the information about the equation of state and the degrees of freedom, what is important in this play. But early on, Star measured the strange quark collectivity, is showing here. This was in already, I think 2006, we already have this data. Both phi and omega show clearly similar pattern as proton and pion. So that shows there's partonic collectivity. It's a very important piece of information for the QGP formation at RHIC. So that's for strangeness. Recently, using star HFT, we also measured D0 V2, showing here after scaling. It also indicate the collective behavior. So this paper, we conclude the results suggest that charm quark also achieved the local equilibrium with a medium in 200 GeV gold-on-gold collision. So that's actually very important. This is the same, as I said earlier on, from the 5th and 6th order of net proton measurement that QCD matter is produced at 200 GeV. So now we ask what happened at 3 GeV. Okay, so let me walk through with you these two plots here. So here we list all the populations for high energy collider energies. They all follow, say, the number of quark scaling. These lines corresponding to fits to different energies. They are all above 0 for the V2 measurement. But from 3 GeV, you see, first, they are negative. Secondly, the scaling for number of constituent quark scaling disappeared. That indicates there's no more platonic behavior. Okay, so this is for V2 measurement. Here, I show you also V1 as function of collision energy for all kind of particles, protons, lambdas, kaon, phi, even cascade here across with a larger statistical uncertainty, of course. And in order to understand this, we also run URKMD. And in this case, in the case of 3 GeV, we have to have a mean field, as shown with a red band here. Only mean field can reproduce the data. Without mean field, it's all fail. Especially this is the case for V2. If you can see V2, if without mean field is positive, but all the observed V2 are negative, showing data are showing here. So I would argue about 3 GeV, or maybe a little bit above, I don't know where yet. The system is hadronic dominant. Above 7.7 GeV, it's a platonic interactions dominant. So this is again, we narrow in a region, in this region for critical search. So collective measurement here also support what I showed in the critical measurement. So most important region actually maybe between 20 and 3 GeV region. Now I move on to B-scan 2. I have one point I will not discuss in detail. Actually, in 3 GeV, we also observed lots of hypernuclei because due to a high baryon density region, but that I will not discuss. That is also very interesting measurement. So for preparing for B-scan 2, STAR carried out actually 3 important upgrades. One important one is ITPC, inner TPC upgrade. So second one is event plan detector. Event plan detector by definition will improve the resolution for event plan. ITPC basically extend the rapidity coverage, allows us to do rapidity scan of a critical behavior search. So, and the third one is the end cap time of flight, I said already. And all upgrades are completed before 2009 and took data actually in 2009 already. This is 3, I will not say too much. And just mention again, this time of flight pieces are borrowed from CBM experiment from FAIR. So all are successful. And we already took data from 19.6, 14.5, 11.5, 9.2, 7.7. We are taking data now for 17.3, hopefully to finish by within a week. And then we'll move on to 3 GeV. 3 GeV. So the plan is to take 2 billion events. So if we, I don't know why, yeah, the plan is to take 2 billion events. So this is to show for 7.7 GeV, which is the last collider mode, we finished the 100 million goal on May 1st. So this is very, very important achievement. Actually, the RHIC detector behaved better than we expected. If we look at globally, what will happen in the high baryon density region, actually there are several facilities are coming up. This is a coverage from collider mode. Alice Farderas, S-Phoenix, and the NICA, that is one collider complex in Dubna. So this will be online in 2023. That's what on the paper they claim. And this is luminosity relative to image scan at RHIC, even at 2. So it's actually quite sizable, roughly 2 orders of magnitude increase in terms of luminosity. But this is a collider, may not be enough. So actually there's a FAIR is also under construction. This is the fixed target. So that's why the collision rate is much higher. And this will be ready in 2025. So I think it's a very important region for us to, if we want to really complete the critical point search to go to fail. So now let me try to summarize. We have clear evidence, direct compared to first principle calculations that QCD matter formed and smooth crossover in 200 GeV central gold-on-gold collisions. At 3 GeV hadronic interaction dominant should be matter, not matter. Lattice calculations say CP may exist for mu B over T larger than 3. So that is in this energy region we need to focus. B-managed scan 2 will provide precision measurements for the energy region 20, below 20 and above, up to down to 7.7 GeV. This is 420 MeV in terms of chemical potential. I think we need seriously the B-managed experiment at fair to confirm first order phase boundary and the elusive critical point. So which is covering in roughly in this region. That's very important. So that is all. So I would like to thank STAR and the RHIC operation. It's very important. Those are the experimentalists whom I discussed a lot for this stand. I would like to mention the stars, yellow, red stars are students currently involved in our data analysis. We have you actually here, Zoe here at Berkeley. And Xiaofeng and Adanga, actually, they were at Berkeley when we started in 2008, this analysis. And those are the theoreticians I discussed a lot during those years. I put a double stars here. Those are the in 2008 INT workshop when we discussed really a lot how to establish the observables. I think we are still benefiting from that day, 2008 workshops. Thank you very much for your attention. That's all I have for today.
Thank you, Neil, for this very nice talk. Questions? Any questions or comments?
I don't see any hand.
There's Vladimir has a question. Go ahead.
Yeah, thank you. Yeah, thanks a lot, Neil, for this nice overview. Yeah, I just had a maybe a small comment or addition to the discussion of fluctuations. Is that there is also, so the STAR has this big paper now since January, which also covers factorial cumulants of proton and antiproton distributions. And I think that two particle correlations of protons and antiprotons are particularly interesting because these quantities have very small error bars in the data from beam-energy scan 1. And I think there you can also see indications that you go into this regime of possibly attractive interactions as collision energy is decreased from 20 GeV to below. And I think it would be also maybe would have been nice to also discuss that plot in addition to high order cumulants, because they are all, I think, related to each other, but somehow the signals seem to be statistically more significant in two particle correlations. So that's just my comment. And yeah, maybe I can also add that we are working on the hydro calculation of fluctuations with Volker, which I hope soon will appear. And I also presented it on SQM, and we will discuss it in some details there. So it's more of a short announcement.
About the correlation, I completely agree. And my take at the moment is I think it's less sensitive, and wait until we have BS2 data analyzed. I think we'll see totally new picture, much better sensitivity. Yeah, we will see that.
Yeah, I'm looking forward to that. Yeah, I just want to mention that. Yes, they're less sensitive, but also your error bars are smaller from beam-energy scan 1, which we have right now, which also makes it convenient for analysis. Even if it's less sensitive, it's also more accurate.
Yes, yes.
Right.
Yeah.
Okay.
Thank you.
Thank you. Any other questions, comments?
Okay. Okay, seems not. Then thanks everyone for joining. Thanks, Nu, for the talk.
Thank you.
Thank you all. See you next week. Have a good day. Bye.